Okay, so welcome everyone to this new episode of EagleFly, the experimental debugger. And yeah, today we're gonna continue on the thing we left off on our research of EagleFly. Sorry, on our research of the IL-32. And yeah, sometimes it's gonna take this long. Well, probably it's gonna take pretty much more time. I think so. To find out a little bit more. There are like 4,744 pages here. Yeah, and of course, we don't have to read the whole ayah, but which is gonna be or probably is useful. We can read the whole ayah if you want. But the whole point of this is to really understand the basic stuff, and this is the basic stuff. If you don't understand this stuff, man, it's like using Unity or something. It's like using some kind of a managed code stupidity there. You don't want to go that route. You want to go this route, and this route is the truth. Is it pure and realistic truth? No abstract stuff, no crazy things. Everything's here. That feels awesome. And there's the way you go. We had to read this and we had to pretty much understand it, the whole thing. Because that's the way it goes. And yeah, so if you would like to follow along with me on this adventure of understanding the IA-32, please feel free to ask any question whenever the stream has ended, please, and I'll be happy to answer them. As well, if you have any doubts, questions, inquiries, anything, just ask me and I'll be there to answer. Okay, so let's continue with this. Let's see what we found out with, because man, this is an adventure, man. You don't know what you're gonna find, man. You don't know. You just have to follow on, and you just have to see what it's in there, because this is a pure processor, Alright. So if I remember, we just left off on this is not this. Okay. We were we had the table for effective operand and address size attributes, which was this this kind of crazy stuff. Well, this kind of a way to manipulate the size for operands and addresses, depending on some kind of prefix stuff. When you use it on the instruction itself with a prefix, you can modify the size for the operand or the size of the prefix, or both, whatever you choose with these prefixes right here. And also you need to this flag encode segment descriptor tells you how these flags will operate. So whenever if it was a 0, that means that the yes or the prefixes will get you to 32 bits, and if it was a 1, the prefixes on yes, the prefixes will get you to 16. And yeah, it's kind of I don't know why they added like this kind of bilateral thing where you have like the same stuff represented by probably it's more because of the semantics, it's like the opposite thing, or I don't know, probably there's more on it, but who knows. And let's see what happens on 64-bit mode. So you can see, I mean, in an instruction per se, you have like this kind of crazy. I mean, you can have this kind of uh, different operand sizes, uh, to different to I mean different operand sizes, different address sizes, combining together to generate an instruction. With these prefixes, which is kind of I don't know, if it's complex or uh, I mean it depends. I mean, it depends on the result. Because the results it's what matters. If the results that it's I mean, of course, the result is going to be affected by the way we combine these prefixes. We need to know how those prefixes modify and affect the result at all. Okay, that's interesting. Please hold me on. I will turn on the lights. Okay. Now let me go to find the instruction format. uh, okay, these are the whole set of instructions. But okay, this is the chapter 3, but I want to go right here. Chapter 1. This is like an overview of the processor architecture advancements across time. Here's the hyperthreading technology. But we don't care too much about that right now. Okay, the point here is that yeah, it says chapter 2, but chapter 2 is like this kind of historical thing. I don't see anything like, oh, is this like this? Okay, we don't care too much right now about that. We care about understanding the basics. Later on, we can see and go on to the registers, which are these extensions to the basic processing units. So the interesting thing about this is that you have these REX prefixes, which there are 4 bits, and there's a bit called W bit, which we can use to modify the size for in 64-bit mode. Also, to modify, um, and also we can use the normal operand size prefix and other size prefixes. Okay, so if we set REXW, the operand size expands to 64. And if we set RE66H, the operand size in 64-bit mode changes to 16-bit operand size. Cool. And we're using SIMD. There's no REX. We use basically 66, F2H, and F3A prefixes to set it appropriately. So let's see. This is the flag encode segment descriptor, and this is the L flag. Now it's not the D flag as before. So now it's the L flag, but the L flag is gonna be always being set. We can have REXW prefix, the operand size prefix to 66H, and the address size prefix to 767H. So in normal default, when being set, it's gonna be 32 and 64. And then when we change address size to 67, it's 32. And then when we say, hey, change me D66, it's gonna be 16, 64. Kept the same, and then this lower back all of them, 16 and 32. And then when we set the W prefix, the REXW prefix when it's set, and we say, hey, no and no, so the operand size is gonna be rewritten by the REX, so it's gonna be 64, and this doesn't modify the address size prefix, so it's gonna be 64. Now if we say, hey, I want the prefix of this will change to 32, and this will change to 64 because we're keeping up to the REXW prefix. Now if we change, if we have, this is the cool part, if we change REX, if we have REXW prefix, and also we have the prefix of 66H, the one that takes charge is the W prefix, so it's going to be 64, and this is not assigned, so it's going to be a 64. And this is assigned, so it's going to be 32, and this is assigned, but the prefix, it takes command, so it's going to be 64. Okay, so this makes it interesting because well, yeah, because the D flag itself was the one that, I mean, it kind of worked differently here, just in the way that prefixes work. I mean, now it's about the precedence of the REXW prefix, whereas here we have this kind of toggling D flag code segment descriptor. Oh, okay. So when it's set to 0, we choose to be 16 by 4, and the flags change you back to 32. When you're this is the default thing, you know, this is default 16, default 32. So yeah, and it's because, yeah, the functionality is different. The operand descriptor, the code segment descriptor D, defines which size, which operand size and address size we'll be working on by default. So that means that normally it's 32, but when the flags are set, it's going to change back to 16 in this case. So they work basically as toggles right here. That's why we were seeing that kind of toggly thing there. But yeah, that's the normal thing. Whereas on 64-bit mode, there's no toggle there. It's like, oh, there's just a precedence for the REXW prefix for the operand sizes, and the address says it can be just 32 or 64, and that's all, depending on the prefix 67H. So, you know, I mean, they are, since the both architectures have different meanings for the things, that means that there's no kind of they're totally different, I guess. Yeah. Now I think about it, I mean, they work totally different. I mean, even though they have like this kind of same, they don't have it in the same spaces. I mean, before yeah, I was wrong on the thing that say before, because I mean, it's not just that they change the sizes, they change the functionality of the architecture. So that's why it's a different architecture. 64 against 32. They work totally different. So it's like, I mean, when I read this thing, it's like learning two languages, you know? It's like learning, oh, you want to learn the 64 and the R32. And that makes totally sense, because, I mean, since this processor especially, I mean, I have the Core i7 6700, and, yeah, I mean, this processor has both instructions being, to use, you know, so we can use both. And extensions, I believe they have SIMD, they have SSC, SSC2. I don't know if he has SSC3, but I know that he has SSC2. Okay, this is getting clearer now. Now that we know about the 64-bit mode and the operand sizes, so now we know, and now we know that operands are by itself the things where instructions operate on, you know. So the operands basically where I don't have these. Oh, I hate because I close it. Let me open back it. Let me open it back again. Let me open it back again. Where is it? Where are you, Mr. Melton? There you go. Yeah, I want to save it. I want to save it. Now I want to go to bin. I want to open that. There you go. Okay. So we had this before, And now I want to say that, yeah, the operands itself, I mean, this is instruction, this this is instruction, and the operands are basically the things that we are operating on. That can be a register, that can be a pointer, it can be a pointer to memory, can be an offset. I mean, it can be a variable itself. It can be anything. Uh, and that's what we define the size of with these prefixes. And the thing that I don't know exactly how is, how do we set those prefixes? Or I mean, are they set on the instruction itself, or are they set on the operand themselves? You don't know. Probably yes, it's in the instruction. All right, so let's continue with this. We have operand addressing, and this is interesting. Because look at this. Every two mentioned instructions act on 0 or more operands. Some operands are specified explicitly and others are implicit. The data for a source operand can be located in the instruction itself as an operand, an immediate operand, a register, a memory location, or an I/O port. When an instruction returns data to a destination operand, it can be returned to a register, a memory location, or an I/O port. So yeah, that makes sense. Immediate operands. Some instructions use data encoded in the instruction itself as a source operand. These operands are called immediate operands or simply immediates. AXP, XCX, SID, SP, and BP. System table pointer registers. Here's the task register. These are XMM registers and the MXCSR. And the FPU registers, search for flame point. When accessing a system register with a system instruction, the register is generally an implied operand of the instruction. The processor contains a selection of system registers that are used to control memory management, interrupt and exception, task management, processor management, and debugging activities. Some of these system registers are accessible by an application program, the operating system, or executed through a set of system instructions. Okay, so those system instructions are interesting. Register operand 64-bit mode. REX, RBP, RBX, RCX, RDX, RSI, RDI, and RSP, RBP through RAR15. Double word, a word, or a low word, low byte. So I'm curious because before, I don't know if I listened that we listened that the high bytes from the ABCD registers couldn't be accessed from 64-bit mode. So I'm curious about how was that possible. I mean, we can use REX prefixes to. Oh yeah, I remember that. Yeah, that we needed to use REX extensions to access from, if I do remember, well, it's from SP, BP, well, SI and DI through R8 and R15, but without the prefixes. We just have ALBL, CLDL, AHBH, CD, and EH. Okay, that. Whoa, where am I? Okay, this is cool. All this is cool. if I can go back onto, well, it was here we go. I don't remember if it was the registers themselves. So these ones, they are, and we have the bytes. Oh yeah, we can access those, but with REX we cannot. Okay, I got it. Okay, and with works it would be the same. We access the 16 bits and the 16 bits, or with okay, cool. The segment registers, which is the same, they are flags register, the x37 FPU registers. Okay, there's another there, that's CR8. And do we have more registers? No, they're the same. MSR registers, which I don't know what's that for. And RDX and RAX register pair representing a 128-bit operand. Okay, so there's a register pair there. So I don't know how this register pair works, if they just allowed to have these two or one register pair, or we can just have any kind of combination, you know. I don't know. We have the memory operands that they can be in 32-bit mode. Okay, this notation is kind of crazy, but it's this just tells us that the offsets are 32 bits or the offsets are 16 bits, and the selector is always going to be 16 bits. in the segment register. Okay, move EAX to the segment pointed by ES with an offset of EBX. That's what that instruction is. Okay, when they use the ESP or EVP register as base register, then we use the stack segment. Yeah, because if they're relative to stack, they would be from ESP or EVP, or they would be on the segment, on the stack segment. The destination of his string instructions. Okay, cool. Here it says, which is a byte placed at the beginning of an instruction. The following default segment selections cannot be overridden. So it's bx, and it moves it from bx to the segment register ds. So we have 32 plus 16, 42, 48. Yeah, that's why it's 48 bit, because it's 32 bits for the offset and 16 bits for the base or the segment selector. And the offset per memory address can be specified directly as static value called displacement, or through an address computation made up of one or more of the following components: displacement, a value of 2, 4, or 8 is multiplied by the index value. So let me zoom a little bit here. Okay, we have a base, which can be in the registers, any register, any common register, and then we have an index times the scale that can be in any register as well. Oh no, it cannot be in ESP, which is the one that holds the stack pointer. The stack pointer can only serve as B, as base, and the index has to be in EBP for ESP specifically, and the others can play all around. It's some displacement, so it's a linear combination of the registers with two a power of 2 and a displacement. So you see this is the vector, the base vector, this is the index vector, which is a combination, and then you have displacement. Well, probably it's more a permutation, these things, and this is a displacement, and the vector displacement, which I mean, yeah, it's more a combination there, yeah. Yeah, it's all combinations. So that's interesting because we have a base for it and a register. The index with exception without ESP times the scale, which can be 1, 2, 4, and 8, plus a displacement. That can be none. It can be an 8-bit, 16, or 32-bit. When the ESP or EP register is used as the base, the SS segment is the default segment. Exactly. In all other cases, the DS segment is the default segment. And what about the where it was the CS? Yeah, the CS segment. Where is the CS segment? You never use CS segment? It's good. It's because DS can be overridden with any kind of. Oh yeah, because DS is gonna be overridden by the one that's more appropriate for the instruction that's gonna be executed. So if you choose DS, then the assembler is gonna choose the at machine level, the instruction, the segment that's gonna be chosen is gonna be the more appropriate for each case. Okay, that's cool. That's cool. So it's a kind of a combinatorial thing, you see? This is the kind of thing that happens. So the index cannot be 0. That's interesting. Oh yes, they can be null. Okay. Each possible combination is useful for data structures commonly used by programmers in high-level languages and assembly language. An important special case for this combination is access to parameters in a procedure activation record. A procedure activation record is a stack frame created when a procedure is entered. Because it automatically selects a stack segment. Okay, so they call it a subscript. Whenever you say, hey, you want this index, I want this element, and I know this is size. Then you have a base plus an index plus a displacement. So yeah, that was the kind of thing that was missing from well, no, I mean, but yeah, I mean that's the reason why you have this kind of 248 bytes whenever you want to access these element sizes. The base and index value can be specified in one of 16 available general purpose registers in most cases. See Chapter 2 Instruction Formatting the Intel 64 Volume 2A. The following unique combination of address components is also available. The instruction pointer plus a displacement Okay, so we already got to chapter 4 and this is getting really interesting. So yeah, that's kind of a special. The RP plus this displacement gets you to like a specific offset from the instruction pointer that's currently on the address of the instruction pointer. And since it's assigned 32-bit displacement, you can go up and down. You know, you can go wherever you want. By sign extending. I don't know what sign extend is. But probably it's just like, I mean, it's just adding it and extending it to a 64-bit value probably. We'll see that what that means. Okay, at the machine code level, All assemblers permit a programmer to use any of the allowable combinations of these addressing components to address operands. So he has okay. So he has 65536 8-bit I/O ports. That means that is like about uh, like a gig. Six five five 36 times a, it's 524k. And you can have also 16-bit ports and 32-bit. Okay, so here we're going to enter to the essence of types. without any additional operand typing. Okay. Okay, cool. The quad word was introduced with the Intel 486 processor, and the double quad word was introduced with the Pentium 3 processor with the SSE extensions. Okay. So the low byte defines is the lowest address in memory, and it's also the address of the operand itself. So for example, okay, here we have oh, okay. So this is the address space 01, 2, 3, 4, 5, 6, 7, 8, 9, A, B, C, D, E, F, and their hex. So that you have the number the number was overflowed because there was not sufficient space for it in this address space. What a shame. It requires two separate memory bus cycles for access. So these are the numeric data types. Okay, so for single precision, the floating point has one sign, and from byte 33 to 3 there's the exponent, and from 022 is the numeron or the mantissa operand, the operand. For the precision, it's basically 52, and from 52 to 62 the exponent and the sign. And there's a double extended precision floating point. Which has an integer bit. And the half precision okay. So we are entering the integer, well, the numeric data types. Unsigned integers are sometimes referred to as ordinals. The signed bit is located in bit 7 in a byte integer. There is this signed byte integer, the signed word integer, the signed double word integer 31, and the signed quad word integer 63. Yeah, that's without that's the value itself, yeah. And then you have a positive value, and the largest number, it's okay, so 7 bits, 1 1 1 1 1, and the smallest is 1 0 0 0 0 and 0 for the sign. And then the smallest number for negative, it's 1 1 1 1, the same, and yeah, it basically goes the other way around, you know. So it's like, let me draw it so we can see it. I mean, basically 2's complement, oh, 2 complement complement, yeah, complement. It tells something like this, you know. I mean, for example, let's put something simple as a sign byte, you know. That basically is gonna be this. You have a bit here and 7 bits here. This is a sign and this is the value itself. So the maximum positive value that it can get is 0 and 7 ones, you know, 1 1, and that's basically 2 to the 7, and it's equal to 2 to the 7, and the minimum, well, it's just 1, so it's 1, or 2 to the 0, it's the same. And then you have the 0 here, and then for negative numbers you have 0 and 0 and for negative numbers you will have a sign bit set on the most significant bit, and the for example, the -1, if I believe the -1, it's uh, it's this, isn't it? Like 1 and 1. This is -1, and the largest negative value, and that this was a tricky way. It was like the misconception about, okay, what's the smallest negative value, and the smallest negative value is -1, because the biggest negative and the largest negative value, it's, I don't know, like something like 1 and 0. Well, yes, 0. Well, let me do it the same way. And this basically is, it was something like, if it's this -1, which means like, I don't remember. There was an equation for defining these values, but basically, I mean, 2 to the 7, and this is like 2 minus, well, 2 to the 7 -1, this, and this is -2 to the 7, you know, because it doesn't include the 0. And yeah, I think that's the way. I mean, also it will continue growing. Now, for example, if you want to say -2 something like 1, all these 1s and this 0, and 3 -3, it's 0, 1. Oh, there was a way to change in a value to from negative to positive, but that was another thing that you just like, for example, you just say like, if you want to change 1 to negative, you just apply a not, and it's like this. Oh, and then you add 1, and this is -1, isn't it? And that's basically the question. You not every bit, and then you add 1 to get the negative number. But yeah, yeah, I think that's, I mean, these are the ranges. All these are, how we just yeah, these are the ranges, and this is a way to calculate the negative number for each one using nots and plus operations. and these are the ranges. It's 128, 127 to minus 128. That's basically 2 to the 7 minus 1, and 2 to the minus 2 to the 7. And then you have 2 to the 16, well, 2 to the 15 minus 1. That's 32,767. And minus 2 to the 15 minus 2 to the 15. And then my 2 to the 31 minus 1 minus 2 to the 31. And then 2 to the 63 minus 1, 2 to the 63 minus 2 to the 63 for a quadruple integer. When storing integer values, and I mean, I just want to mention that there are many ways to encode negative numbers. There's other ways that basically you can like do this thing, but instead of setting this minus 1, it could be something like this, and zeros. And I mean, just telling you that, I mean, like this bait, it's tells you if it's a negative or a positive number, but that would mean that's not like super efficient, because you have 2 negative zeros, you know, because you can say something like this, for example. Which with 2 complements you don't have 2 negative zeros. So this is not 2 complements. This is I don't remember the name, but it's another way to encode negative numbers. So yeah. So yeah. When storing integer values in memory, okay, so they are indefinites when operating on x87 FPU. But I would say that that was good for today when we finish with integer values, and on the next one we will continue with floating point data types, which is gonna be crazy as fun, you know. So yeah, I mean, you know, guys, you know what, where this is going. So please, if you have any question, ask them. Feel free to ask them, and I'll be there to answer. Yep. I think that's it for the day. And yeah, you can ask the question on Twitch, on Twitter, or on YouTube, as I mentioned at the beginning of the stream. And yeah, I think that would be all for today. We are uncovering the mysteries of the IA32 right here and right now. And yeah, I think that's the way it goes. So thank you very much for coming, and I will see you all on the next stream.